start recording. Good morning, everybody, again. And yep, recording in progress. And thank you very much, Bernardo, for the screen share, for the Moodle link. You can tell I'm really preoccupied with trying to get things done. Right, now let's see, why is there a Google Calendar? Ah, okay, good. That should not be on here, but hey, let's go over there. Oh, good, great. Now, can you see my my screen? Can you see the Excel starting point and my wonderful impression of a butterfly? Excellent, so everything works out quite well. Yes, it's butterfly, and there is a reason to that, because today we are going to deal with butterflies. So it looks like everything is good, and I don't need to worry about things. Although there's a little bit of lag, but hey, that's all right. And as long as you can hear and see everything properly, then absolutely fine. And you are aware of the assessed practical for this module for the BI 308. I think I posted the website, and some people have already finished task 1, 2, and 3, and you should be perfectly capable of doing so by now. If not, the link to the website with the practical is on Moodle, but also in the announcement of for this module. But check out on Moodle, there is a big link to the assessed practical, and the first 3 parts you can do very easily. And the tasks are like questions. And I think some people, as I said, some people have already completed it, very much to my surprise. You're not supposed to do that, but if you can do it, and even better. So there are little tasks where you actually do a little bit of scientific work in terms of discovery of a new and exciting drug. And for that, you need the tools for this, for data analysis. Okay, so let's get started. Again, most wonderful good afternoon, morning, whatever you prefer. I know we've got people in different time zones, so doesn't matter. And what I'm going to do with you today is I will do a quick revision of the binomial that we've done, of a binomial test that we've done yesterday. Not yesterday, last week. And then we will move on to what is very, very useful. This is this goodness of fit test. And that's a really, really useful test for scientists. And you probably have experienced that because this is also known as one of the chi-square tests. So with the binomial, I tell you what we do. The easiest way to illustrate how these things actually work is with examples. And I would like to choose an example. And as you can see here, this beautiful drawing, I'm not an artist, this beautiful drawing of a butterfly, there is a purpose behind that, because we will use a butterfly or butterflies to illustrate what these different tests actually do and how we can actually apply them. So it will be a little bit spring-like with the butterflies. And let's start with the assumption that we do an experiment. And I have to say, no butterflies were harmed in the course of this experiment. we look at a population of butterflies, and we found that 35 out of 100 butterflies, so we sample 100 butterflies, 35 out of these 100 butterflies are red. So they are red, and we know that the color in butterflies is determined by the A allele, so A or capital A allele. That is responsible for the color. So butterflies that are AA are red, and everything else, let me write it like that. They are all, let's say, they are blue. So we sampled 100 butterflies, and we found 35 are red. So, of course, the first thing that we, in a way, we want to know is what is the proportion? What is the proportion of red butterflies in the population? What is this proportion? And since we're dealing with a proportion, we know that we are looking at binomial distribution. Proportion usually hints binomial, and we have only two potential outcomes, namely red and blue. So these are two categories. We have count data. We count the butterflies, so we've got 35 and 100. And therefore, we know that we are working with something binomial. So I just got in the bus like 8 minutes ago. And we could say, okay, we assume that the proportion of red butterflies in the population must be around, let's say, 35% or something like that. This is just simply because our sample is 35%, but it doesn't mean that the exact proportion of reds in the population is indeed 35%. It could be, say, 29% or maybe 38% or something like that. So how do we actually find this out? Now, I showed you last week that we basically have two options. We can either, so we can calculate a 95% confidence interval, 95% confidence interval for this proportion. You see, that's the good thing. When I'm on the computer, I can't hear anything.
दाएं इधर आएं प्लीज. मेरे कंप्यूटर से आवाज ही नहीं आ रही.
Okay, so what's the 95% confidence interval for the proportion? I showed you how we can actually do it by hand, the calculation. And we said we can use this, what is called the Wald correction or Wald amendment. in which we add 2 and 4 to our numbers. So we would get 35 plus 2 divided by 100 plus 4. For our proportion that we use, and we can say plus minus 1.96, and we will soon find out what is this special thing about this 1.96 when we are talking about the normal distribution. And we take the square root of 37 over 104 times 1 minus 37 over 104. And we divide this by 104. And we take the square root of this expression here. Okay, so this is the equation that we would say that is for our confidence interval. If we want to find out what is the proportion of red butterflies in the population. So we can do that. We can try and calculate that. And according to my calculation, we would get 0.356 plus minus, when you do this calculation, what do we get? 0.092. Okay? And obviously you can try to do this calculation if you've got a calculator, or and the reason why we add this 2 and 4, this is what I said last time, this is a sort of a correction. If we've got fairly small numbers, then we add these numbers 2 and 4, because it could happen that we've got 0 in one case, if we don't measure any butterflies, and the whole thing breaks down. And it has been sort of it has been established by the statisticians that these numbers 2 and 4 actually give a pretty good description of this confidence interval. Okay, so we can do this calculation, and we can find that for the population of the red butterflies, we find in the population it is somewhere, well, 0.356 minus 0.092. So that would be 0.264, and also 0.356 plus 0.092. That gives us 0.448. So this is basically the lower bound here, lower bound, and this one here is the upper bound. So we can say we are pretty confident that the proportion of red butterflies in the population is somewhere between 26.4% and 44.8%. And I've just expressed these numbers in percentage. And the 0.092, that is what happens if you multiply this part together. So this one here, the 0.356, that is this part here with rounding, and plus minus 0.092. This here is actually also called the margin of error. Margin of error. And where this 1.96 comes from, that is something we discuss in another session. Just simply accept it at the moment that this is a number that is quite important in statistics. Okay, so this is the proportion of red butterflies in the population. It is somewhere between 26.4 and 44.8%. So that is what we would see. Now, of course, we can move a little bit further with that. We can, for example, ask, what is the frequency? What is the frequency of the A allele in the population? Let me write this down. In the population. We are not yet there with the Hardy Weinberg, but you are absolutely right. We will come to that in a moment. So what do we know? We know that we have only the combination A gives us the red color. This is what I told you. AA, lowercase a gives us the red color. And we know that AA will show up with a frequency of 0.264 up to 0.448. So all we need to do really is we need to just simply, if we want to know what A is, all we need to do is we need to take the square root of 0.264. Because then we get one A, multiply it with another A, and we get 26.4. And likewise, we get square root of 0.448 for the upper bound. So if we do this calculation, all we need to do is the square root. So we get the frequency of A would be, so I do the square root of 0.264, and that gives me, what does that give me? Square root of 0.264. What is the square root of 0.264? Got anyone a computer, calculator, or Google? Thank you very much. That is 0.514. And lovely, thank you. And what do I get if I take the square root of 0.448? So that gives me 0.669. So the frequency of the A allele in the population, lovely, thank you, in the population, the frequency is somewhere between 51.4% and 66.9%. Does that make sense so far? Are you happy with that? Excellent. Have you actually done these calculations with in the BI324 module with Dr. Ellis? Yes, you have done it. Excellent. And he also showed you how to apply the binomial. Aha. Now, of course, we could now also calculate the frequency. We can do the frequency of the A allele in the population. But at least now you see how you actually get these margins. So you don't have to believe everything, you can do the calculations yourself. We can do the frequency of the A, of the capital A allele, because we know that lowercase a plus uppercase a add up to what? Absolutely right. It adds up to 1, 200%. So that's very easy. So all we need to do is for the A allele, for the capital A, we just simply calculate 1 minus 0.514 and also 1 minus 0.669. And that gives us the frequency of the capital A allele. Okay? And we can do that. So we would get for this one here, we get 0.486, I believe. And this one here would be 0.331. Or we can write it conventionally in the other way around, because usually it's the smaller one, that's the lower bound, that's written first. So we just write it as 0.331 and 0.486. And the reason why it equates to 1 is because we only have lowercase a and uppercase a, and they make 100%. So this one is the same as 100%. So that is the frequency of the A allele of the capital A in the population. We are pretty sure that it is between 33.1 and 48.6% in the population, whereas the lowercase a is between 51.4 and 66.9%. And this was a really nice application of the binomial equation that I've given you. Now, of course, you can do it by hand, these equations, or you can use this online calculator that I showed you. Let me just quickly move over to that. Where are we? We are here. And wait a moment. I want to share. Where am I? Oh yeah, here it is. Can you see the online calculator here? Yep. So here I put in 35 for my A, and I get my 26.4 to 44.7. This is the lower bound, this is the upper bound, so I don't really have to do the calculation here. Does that make sense to you? So you can use this online calculator, or you can actually use the calculations by hand. Either way is absolutely fine. And what I said earlier, by the way, if you don't have a calculator but a computer, well, maybe in an exam, you have to do it by hand, perhaps. However, let me just show you a little trick that a lot of people don't know. If you've got a PC or something, or even tablet, but don't have a calculator, you can very easily use Google to do calculations for you. So in the address bar, you can just enter 30. I just make something up. 34 times 56, and look at that. It comes up with a calculator and even gives you the result. So you can use Google to do this kind of calculations, and you can also do an online calculator if you don't have anything at hand to do calculations. I think that's quite a neat trick, and it's worth knowing. Now let me go back to the other screen again, because we can do a little bit more. Okay, so we are back on the Excel screen, aren't we? Thank you very much, Ed Miller. That's very good. That's the chi-square test calculator website. And as I said, I would certainly bookmark this. Now, let's go a little bit further. We've calculated our alleles, and we have now looked at the proportion of red butterflies in the population, and from that we got our allele frequencies. And now we go a little bit further and we say, okay, let's do a little bit further analysis, because we found that we've got AA, that gives us a number of 35 that we analyzed. And we also analyze, we look for the other genotypes that we have. And we found the heterozygotes, which are either lowercase a, uppercase a, or the other way around, uppercase a, lowercase a. We found them to be 55. And we found the homozygotes for capital A. We found them. What would that be? How many did we find if we looked at 100? 10. Absolutely right. So we would have 10 of those. Okay, so that's quite easy. And we can now say, right, is this actually this distribution of the genotypes? Is this distribution of genotypes, is this what we would expect? Or is there anything weird going on? So let me write this down here. This time I do it properly in Excel. So we've got 35, 55, and 10. And just make this a little bit bigger so that we can see that. Okay, so these are our genotypes here. 35, and I'll put down here, that's AA. That is the heterozygotes. And here we have AA. Is this population, is this distribution of the genotypes what we would expect? What do you think? Does it look like a proper distribution, a proper genotype distribution? Or is there something strange going on? What do you think? Where did the 10 come from? Well, I told you we looked at 100 butterflies. So we had 35 and 55, and therefore this 10 must be. Can we actually quantify that? So people suggest there is something weird going on. Interesting thoughts, very interesting. So in a way, people already have a slightly uneasy feeling about these numbers here. Am I right? It sort of is. Actually, what would we expect? And Lucy and Juby are going in the right direction. Shouldn't be the homozygotes, the lower AA and the upper AA, shouldn't they be the same numbers? What do we expect? Well, and now here, Hardy-Weinberg comes into play. Because what does Hardy-Weinberg actually say? Hardy-Weinberg says A plus A squared. This is what we would expect, and that would be 100%. So if we multiply that this bracket, if we square it, we get a squared plus 2 lowercase uppercase plus uppercase squared, right? Is that correct? For Hardy Weinberg? Brilliant. So we would expect a ratio of 1 to 2 to 1. And you have done that with Dr. Ellis, haven't you? Ad nauseam. So we have 1 to 2 to 1. Now, how would that be expressed if we had a total number of 100? So if we had 100 butterflies, how would this be expressed? Absolutely right. We would say that would be 25, and that would be 25. And the heterozygotes, of course, would be how much? So that would be 50. Because the heterozygotes are twice the number of the homozygotes. Absolutely right. So this is what we expect. Now, this is what we observe. And what we expect, these are the numbers that we expect. So we expect 25, we expect 50, and we expect 25. And I make the numbers larger again. Did I use 36? So let's do 36 here as well. So these are the expected numbers. Here are the observed numbers in this column here. Here are the expected numbers. And what we can do now is we can do with these numbers, we can do what is called a goodness of fit test. Goodness of fit test. And the goodness of fit test, it's a modification of what is called the chi-square test. And this sort of X with an attitude, it's not because I'm pissed and can't draw straight lines, but this thing is the Greek letter chi, which actually symbolizes an X more or less. You've done the goodness of fit test with Dr. Ellis? No? So what this goodness of fit test actually tells you is what is the probability, to get the observed numbers, to get the observed numbers if we have expected numbers. if we have the expected numbers. And we try to figure out what is the probability to get these numbers. Where's my pen? There's my pen. What is the probability to get these numbers if we actually expect these numbers here? And I show you first how you do that by hand, because it's not terribly complicated. First of all, we set up a null hypothesis. Null hypothesis in this case says there is no difference between expected, or I should say between observed and expected numbers other than caused by just simply sampling error. Other than caused by sampling error. So any difference that we see here between the 35, 25, 55, 50, 10, 25 is just simply down to sampling errors because we just look at a sample here. The alternative hypothesis would be there is a difference between the observed numbers and the expected numbers, and this can't be just simply explained by sampling error. So how are we going to check whether we should believe the null hypothesis, whether there is no difference? So we calculate the probability to get these observed numbers from the expected numbers, or we calculate the difference. How do we do that? So we can calculate this chi-square factor, the chi-square number, and the equation for that is we take the sum of observed numbers minus the expected numbers. We square it and we divide it by the expected number. Now, I know that a lot of people start hyperventilating when they see something like that. So let's just simply try to figure out what this means. So let's start with the AAs, with the lowercase, with the homozygote A's. We have observed number, that is 35 minus 25. We square it and we divide by the number of the expected. So that's 25. That's the first part. Plus, now we do the heterozygotes. We have 55 minus 50 squared divided by the number of expected. That is 50. Plus, now we do the homozygotes, uppercase A, that is observed minus expected squared divided by the number of expected. Are you happy with me? Are you happy with that? Not with me. This is basically what this equation says. Does that make sense? So that is really the equation that we need to do in order to get this number. And this number can then inform us about what is the probability. Right. So let's do the calculation. So 35 minus 25, and John already did it, so you are absolutely right. That is 13.5. You're absolutely right. For people who are not so fast, 35 minus 25, that is 10 squared over 25, plus 55 minus 50, that's negative 5 squared, is 25 over 50. That's right. Plus 10 minus 25, that's negative 15. Squared is 225 over 25. So here we get 100 over 25, that's 4. Plus 25 over 50, that is 0.5, and 225 over 25, that's 9, and that actually gives us a value of 13.5. So this is our chi-squared value. Chi-squared value is 13.5. Have I done it right? Well, John says that it is 13.5, so I fully agree with him. The 225, negative 15 squared divided by 25, that is the number for our AA, capital AA. Maybe I can write this here. Absolutely right. That's absolutely correct. Thank you very much. Yes, totally right. So what on earth does this chi-square value tell us? Now, we need to sort of calculate this value. We need to translate this value into a probability. And how are we going to do that? Well, actually, there is an Excel function to do it, but instead of showing you this Excel function, I show you something that's much easier. And I assume you are happy with easy, right? We all want easy. Let's make this a little bit bigger. Again, these are our numbers here again. These were the observed. And these were the expected numbers. Now, the great thing about Excel is that, again, we can use a built-in function in Excel to calculate the probability that we get these observed values when we expect these numbers. And the function in Excel is just simply equals chi-square dot test. So let's see what we get. Let me make this bigger again so we can see it properly. So equals oh, look at that. We already come up with some suggestions. chi-square test. I double click on that, and then it asks, what is the actual range? Do you see this actually? Do you see this little window thingy? So it asks us basically, that's interesting. It asks us what is the observed range and what is the actual range, and what is the expected range. Do you see the numbers that are put into this chi-square? Do you see these numbers, D146 to D148? Yes? So these are the numbers, or these are the cell references. The first part, D146 to D148, these are the observed numbers, that's in the D column. And the F numbers are the expected. So I just put them in, close the bracket, and I get my p-value. And again, I make this larger. Let's see. Okay. Here is my p-value, and now I make this large. My p-value, my probability, my p-value is 0.0011. Or if I move the decimal, it is 0.117%. There is a 0.117% chance that I get these observed numbers when I expect actually these numbers. It's rather unlikely that we get these observed numbers. And if we say anything below 5%, that is what we would use for a 95% confidence interval. Anything below 5%, and that is our significance level, we know if p is low, that is the chi-squared value. And I might show you how you can translate this value, but we did a sort of a shortcut and basically asked Excel to calculate it. I might show you in another video how you can translate this into exactly the same value. I just wanted to show you the calculations that you can use. So if P is low, if P is lower than 5%, what happens to H naught? If P is low, H naught must go. Exactly. We reject our null hypothesis. In this case, P is very low. Okay, if you really must know, we can convert this. P, we can convert this 13.5. There's an Excel function. It's the chi-squared dist function. And we put in 13.5 Okay, let's just simply forget how we get from the chi-square. I do a video how you can get from the chi-square value into the p-value here, but what we've done is just simply used the Excel function chi-square test to get this p-value, which is much easier than do all this weird calculation. I just wanted to show you how you calculate that. But what we see is the p-value is very low, so we reject the null hypothesis. We say, well, we can't believe that there is no difference between the observed data. So there is indeed, we can say, there is a difference. It's useful to have it. I will not ask you to do that, but it's useful to have it. There is a difference between observed and expected data. Which cannot just simply be explained by sampling error. Which cannot be explained just by sampling error. So there must be something else by sampling error. So very clearly, this means that AA is the capital A's, the homozygotes for A are underrepresented. There is something weird going on with these AAs. What could it be? Mutation? Unlikely. Natural selection? Yes. Why? How? Yes. They provide an advantage, or you can turn it around and you can say there is likely that the homozygote, capital A's, provide a disadvantage. And therefore, the individuals with this constellation are less fit. They have a lower fitness. This could be, for a variety of reasons, but in this case, it looks like that the homozygotes, capital A, have a problem. Or it could be that there is a problem with Hardy-Weinberg, but you would be hard pressed to explain why this actually is. So you have seen how we can actually use data analysis to calculate the frequency of an allele in the population and also check with this goodness of fit or chi-squared test. With this goodness of fit test, if there is anything weird going on in the in the genes, what we observe compared to what we expect. So next week, what we are going to do is we can probably expand on that and say maybe we can find out what's wrong with these butterflies with these AA. Maybe there is a link to something. And that will be a continuation of this chi-square test. I'm way over the time. I apologize, but I hope you found this interesting, and I will put it up on Moodle as soon as I can. So thank you very much and enjoy your afternoon. Go out a little bit. It is a glorious day, even without butterflies. Thank you very much. See you around. And if this dog farts again, I swear to God. Stop recording. Oh, I shouldn't have said that. Stop.